So we're going to spend a little bit of time talking about circular motion now. And today we're going to talk about a special kind of circular motion, which is real common and real important. So we're going to spend some time on it. It's called uniform circular motion. When you're in uniform circular motion, we're going to find out that we can define something called the centripetal acceleration, and then we'll do some examples. So uniform circular motion is moving in a circle with a uniform speed. And so that's, uniform means your uniform speed, uniform radius, and you're moving in a circle. So what does it mean? How do we describe it? And what can we learn about it? So we're going to talk about that now and hopefully get ready for class. So let's start out here. So here we have a car moving in a circular path, moving at a constant speed. So it's going like at 55 miles per hour. Is the car accelerating? So think about this and we'll talk about it. Okay, so hopefully you got yes. So this is a tricky thing, I think, and the key here is that, acceleration or velocity rather is both speed and direction. And so in this case, the speed is the same, but the direction is constantly changing. And so if you change the direction, you're going to be changing the velocity. And a good rule of thumb that I'll probably bring up in conversations like this is that when you're accelerating, you feel it in your body, right? When you hit the gas pedal and accelerate up, you sort of get pushed back into your seat, right? You feel that acceleration. When you put on the brakes to slow down, you sort of get pushed forward, you feel that. And by the same token, when you're turning, right, changing the direction of your velocity, even if your speed stays the same, you feel that. Okay, you feel that acceleration, right? So the way our text talks about it is it talks about inertial reference frames and non-inertial reference frames. I wouldn't get too hung up with that, but basically a non-inertial reference frame is one where you're accelerating. And so you can generally feel those accelerations. And so let's look at this now. So now we want to kind of unpack this a little bit. And so here we're looking at two velocity vectors. One's the initial, one's the final. And so if we want to look at A, B, C, or D, which one gives you the correct direction of the average acceleration during whatever time interval this was? So we got to do some vector stuff here. So give this a go and we'll talk about it. Okay, hopefully you got choice B, and lots of ways to do this, but how I chose to do this is sort of like this right here, using our sort of head to tail path business. And so what I'm saying is, in this case, is I want the vector VI plus the change in the velocity, the delta VI, to equal my vector V final. And so in order to do that, I wrote VI this way and V final this way, and so the delta V points in a direction kind of like this here. And so now let's try to take this and think about this situation. So again, we have this car circling around some point, moving at a constant speed. What direction is the acceleration at this particular moment? So think about this and see what we think. Okay, so hopefully you got C. So what that means is that the acceleration that this car feels is towards, we're going to find it's going to be towards the center of the circular motion that the car is doing. And so what we're going to draw on here is that example we just did. So I'm just going to take 2 points. Here's my initial point. Here's my final point at some distance. Again, we're assuming uniform circular motion. So constant speed moving in a circle of constant radius. And we're doing this over some delta t. And so if you look here, this is the exact same picture of vectors we just did. So hopefully that is sort of helpful. I think when you first see this, it can be tricky to kind of actually visualize how this acceleration works. Even I've seen, it before where people know that the acceleration points towards the center, but it's kind of confusing. And the way I think about it here is if you think about, so initially your velocity is this way, right? If I want to get my velocity to be over here, I've got to have an acceleration that's going to point in towards the center, right? I've got to pull on this thing to make the velocity sort of come out this way. And you can visualize it a little bit better if you even make this a little bit more extreme, like a case like this here. Hopefully it makes sense that the direction of the force that's going to get VI to V final is one that's pulling in towards the center of the circle. And of course, as you make this angle smaller, it'll get to be more and more perfect of a sort of an example, but hopefully you can kind of see that. And in most of the situations that we'll be applying this to, you'll be able to find the force that's responsible for pulling in towards the center of the circle. So again, even when I make these velocities smaller and smaller, my delta v, right, which of course my acceleration, the vector, is delta v divided by delta t, is again pointing towards the center of the circle. And so that's our rule. Acceleration is going to be towards the center of the circular path. And so this is tricky. Sometimes you'll have problems where maybe the object, we'll see one in a little bit, is only sort of partially on that circle, but you can still use this idea of uniform circular motion. So now what we can do is unpack this a little bit more to try to get the magnitude of this acceleration. So again, we're looking at this special case where we're constant speed moving on a constant circular path. And so here, so now we'll go sort of the other direction just to kind of set our picture up. And so we got two vectors, the two radius vectors, which have the same length but are moving, and then v1 and v2. So it's going to be key to us that basically these here are making 90 degrees. So the velocity is always tangent to our path. And so what I can set up here is between v1 and v2, this is my delta v. So again, you know, if we just think about head to tail, this is my v1, and then the delta v is what gets me to the v2. Again, you can see that that's going to be pointing generally in towards the center of the circle. And so what we can do is look at this for very, very small angles. Now, I'm not going to draw it very small because then it's hard to see, but just assume that this angle is very small. And so we've got this picture here that we just sort of talked about. So the v1, the v2, and the dv is the result after you move some angle theta. But what I can also do is look at this triangle here. And so again, we're assuming that the theta is very small. And so if the theta is very small, I can make another triangle here and make the approximation that the length of that triangle is v dt. Now, you know, in reality, that distance that we're traveling is more like a circular arc. But if it's a really tiny angle, then you can approximate it by a straight distance. And how did I get this? Well, it's just the velocity times that little tiny bit of time, right? Velocity would be length per time, you know, meters per second. And if I multiply that by time, it comes out as units of a length. And so this would be how we would express this distance. And again, it's more of a circular arc, but because we're making this approximation of small angles, it works out this way here. And what happens is these two angles will be the same. You can see that again, you know, because of that important distinction that the 90 degrees between the R and the V1 stays the same. And so I can take these. Now here, I'm just going to make this triangle and sort of think about, you know, this as just being the magnitude dv. But now we can take these two similar triangles and use them to try to figure out the magnitude for this acceleration when you're in uniform circular motion. And so here, I'm just going to say, well, the ratio of dv to v should be the same as v dt to r. So this ratio should be equal, again, because these are similar triangles. And so if I take that, you can just sort of rearrange things a little bit and get dv dt equals v squared over r, and then just sort of realize that, you know, dv dt is our magnitude of the acceleration. So again, this is such an important acceleration. We call it the centripetal acceleration. So this is the acceleration. Again, we're looking at uniform circular motion, and it's v squared divided by r. This is the kind of thing that's going to pop up a lot, and so that's why we're going to spend some time on it. And again, the direction is towards the center of the circle. So here I've got my accelerations towards the center of the circle, and the magnitude is v squared over r. So now what we're going to do for a little bit is we're going to use what we've learned about study of forces in situations where uniform circular motion is happening. And our acceleration will end up being this v squared over r. And so we're going to be able to get insight into a lot of different kinds of systems that way. So let's go ahead and try to explore a couple. So here's an example. Let's read it. The bobsled track contains turns with radii of 33 meters and 24 meters. In which turn will the bobsledder feel the greater acceleration? And for this problem, assume the bobsled has constant speed. And so this is an example like I was talking about where the bobsled doesn't move through the circle the whole time. It sort of moves through a portion of the circle, but we can still use that with our physics to try to understand that portion of where it's going on. So go ahead and give us one to go and we'll talk about it. Okay, so for this one here, I got 24-meter turn. So let's unpack this a little bit. So here we can actually just go through and calculate. So again, we're assuming that the bobsled is moving with a constant velocity, as we were discussing before. And so what we can do is use our equation a squared or v squared over r. And so for the first turn, that would be the 34 divided by 33, and you get an acceleration of 35 meters per second squared. And for this one, 34 divided by 24, you get an acceleration of 48 meters per second squared. And so again, it's good to sort of stop and think about this equation in regards to this example here. So hopefully this, when you get this acceleration, centripetal acceleration, it makes sense to you. First of all, it makes sense that the faster you're going, you would feel a bigger acceleration, right? If you make a turn going really, really slow, you don't really feel it. The other thing is this R is kind of tells about how tight the turn is. And so in this case here, when you're going through this second turn, it's a much tighter turn. You're doing it with a much smaller radius, and so you're going to feel a larger acceleration. Hopefully that makes sense with your experience as well. Now, what we've done here is what they'll do oftentimes is you express the acceleration in terms of g. And so you've probably heard people do this before. And literally you just take that number, like that 35, and divide by 9.8, and that gives you 3.6 g. So that bobsledder in that first turn, the acceleration that they're feeling is 3.6 times the gravitational acceleration. It kind of gives you a sense of, in something that you experience, which is the gravitational acceleration, sort of how big it is. And that second term is like 5g, so it's a much more extreme turn. So we'll oftentimes the problems will ask you to do that. All right, our next problem is a car on track example. So we sort of started with this one here. So you have this car traveling around the track. So it's a car of mass m is driving around a circular track with a constant speed v. If the coefficient of static friction is mu, what is the smallest radius the track may have before the car starts to skid? Assume the track is level and not inclined in any way. And so this is the kind of problem that you'll have. And again, it's sort of combining this new aspect that we're talking about, circular motion, with hopefully some stuff that we've been working with from Newton's laws. And so the first thing we always want to do with a problem like this is to kind of figure out the forces. And so I'm going to draw two pictures. There's this bird's eye view, but I'm also going to draw sort of a picture. So here's the car, and then here's sort of the center of the circular path, right? So we'll call that maybe like point A or something, just as a reference. And so in this picture, I'm kind of like, it's like I'm standing here looking at the car. And so you look at the car, the forces on the car. Remember, our first step is we find our car. Let's call this our x and y axes, like so. And so if I was drawing them over here, just to kind of reference how we're doing this, is I would call that would be my x direction, and my y direction would be pointing out at you guys. And so that's how we're sort of looking at this here. And so the forces, there'd be the force normal pressing up, and then mg of the car down. Now there's a static friction, and this is where the tricky part is, when you're doing these problems, is which way is the static friction going? Well, again, in this case, we know that our acceleration is in towards the center of the circle, and so our frictional force is going to be in towards that point A. And this is the part that I think when you're first doing these problems is really tricky, is sort of accounting for that. And that's the part that can be a little bit difficult, I think. And so let's look here then. So a car of mass m is driving around a circular track with a constant speed v. What force provides the centripetal acceleration required to keep the car moving in a circle? Again, assume the track is level and not inclined. So go ahead and think about this one, and we'll talk about it. All right, and hopefully you got the static friction, right? And so that's what we were saying over here. It's that frictional force that's going to be accounting for that centripetal acceleration. We know that when this car is accelerating, there's going to be a net force in towards the center of the circle, and the only force we have that can account for that is the friction. And so what we do then is we can, let's go back to this picture here, and so we can then do our F equals ma. So maybe I'll change the color just to kind of, and so our F equals ma in the y direction. So Fy equals, that's going to be 0. The car's not moving in the y direction, and so as will happen often, from that we can get the normal force is equal to mg, and then in the x case, right? Over here, we know that the only force here is that frictional force. And so that's going to be responsible for m times a. And this is one of those cases where, this equation is kind of ridiculously easy, but getting there is the hard part, sort of being sure that these are the only forces that are acting in this x direction that we set up over here, and that's what's going to take some practice. But again, now when you have this, we can say, well, I know that my frictional force, the maximum, so that's what we're interested in here. We want to know is, what's the smallest radius before the car starts to skid? And so we're just going to say, let's maximize this frictional force to be mu s times the force normal. So that's the biggest it can be, and so we'll start with that. Now, as happens often, not every time, but often, the normal force is mg. So we can plug in this mg over here, and what's nice is cancel out the mass. So this doesn't depend on the mass of the car, and that should make sense, right? Because when you make tracks and stuff like that, you're not, they have different kinds of cars riding on there and stuff like that. So it kind of makes sense that the mass wouldn't be important. And so we can get here acceleration equals mu s times g. And so I'll call this the max. So this is the maximum acceleration we can have is mu s times g. And so our last step would be, well, we know that when we're moving in a circle, we have centripetal acceleration, v squared divided by r equals this mu s times g. And so what they wanted to find here is the smallest radius that we can have before the car starts to skid. And so I just literally go through and solve this for my r. And so when I did that, I got v squared over mu s times g. So I just basically replaced the r in the mu s g like that. And so that's the again, the smallest radius the track can have before the car starts to skid. Now, in discussion this week, you'll do a question where they incline the track. And so this is what they do for like race cars and stuff. And so you'll be able to adjust that radius a little bit by using some sort of an incline. So we didn't do that here. We did sort of a simpler case. Okay.